Okay, this is the weekly reading questions number 9, and this is an important one. I mentioned in my study guide that I wanted you to be able to calculate residence times, so that's the nature of the first question. Use the figures below to calculate the residence time of carbon in the atmosphere, land biosphere, ocean mixed layer, deep ocean, and rocks. And so as we know, to calculate the residence time, we need the reservoir value, and the fluxes. And so the reservoir value for the atmosphere is 864 gigatons of carbon. And the fluxes in and out are going to be 110 plus 60. The fluxes in are 110 plus 60, and the fluxes out are 110 plus 60. So that's 170 gigatons of carbon, and those are fluxes, so that's per year. And the way the units work is that these cancel out, and then you're left actually with 1 over years, which is actually years. So the units of this come out in years, and for the atmosphere we get 5.1 years. So I'll just put that over here. We can redo that calculation for, we can redo that calculation for the land biosphere. And just give me a second to get rid of all this stuff. And so the land biosphere, on the other hand, is a larger reservoir. It has a reservoir of 2,150 gigatons of carbon. You can see that right here. And the fluxes in and out of that are 110 total. And so this, if you do the math, equals 19.5 years. So we'll put that over here. 19.5 years, a little bit longer than the atmosphere. So the average molecule of carbon lasts almost 20 years in the land biosphere, primarily because trees are big and takes a long time, takes 20 years or more to grow a full tree, and so that's what sucks up that carbon. Now the ocean mixed layer has again, the ocean mixed layer contains about as much carbon as the atmosphere, 900 gigatons, and you can see that it also has 160 flux in and out, both 60 here and 100 here, so that's 160 gigatons of carbon per year, and out of this we get 5.6 years. So we'll put that up here. So we can see all the residence times for these top 3 here. The atmosphere, the land biosphere, and the ocean mixed layer are all pretty small, or pretty short times. Now let's get to some of the bigger reservoirs. Now as soon as this reservoir gets large, we go to the deep ocean, we have 37,100 gigatons. And the flux out of that is only 100 gigatons of carbon per year. Still a pretty big flux, but it's a large reservoir. And so out of this, we get, if we divide 100 into 37,100, we get 371 years. So all of a sudden, when we start to deal with these large reservoirs, we see that the residence time goes way up. So now let's finally look at the rocks. And the rocks have millions and millions of gigatons of carbon a year. So I'm just going to provide a lower estimate of that by saying let's just assume the rocks are only 1 million. But you'll see that this is just this is a low value for this. But since the flux is so low, then this is 10 million years. That's 10 million years. And so the longest residence time is obviously rocks, and the shortest is obviously the atmosphere, although the ocean mixed layer is really pretty close too. But according to our calculations, those are the shortest and the longest. Okay, now let's go on to the next problem. This is kind of a difficult problem, but it says which of the following processes involves organic carbon? And so I'm just going to go through these and try to answer these. So if we look at the precipitation of a calcite skeleton, that's an inorganic process. So I'm just going to put inorganic here. And that's because some ocean organisms combine calcium and bicarbonate to make calcite. They make calcite shells, and even though the precipitation is formed by living creatures, the process is inorganic. The exchange of carbon between the oceans and the atmosphere, this is tricky because the exchange is driven by an inorganic process, that is the dissolution or diffusion and off-gassing. Because some of the CO2 in the atmosphere, however, this exchange involves organic carbon because some of the CO2 in the atmosphere is actually produced by respiration. This CO2 then dissolves in the surface ocean, but its source is organic carbon. So it's an inorganic process, but it involves organic carbon. Off-gassing can also contain organic carbon from organic material that is decomposed in the ocean. So it's that's kind of a tricky one. So that too is an inorganic process. If I can spell today, hold on. Inorganic. And now dissolution at the seafloor. This is essentially the opposite of precipitation. So it too is an inorganic process. And weathering of organic carbon in sedimentary rocks is an oxidation process. This type of process involves organic carbon. So what I should say is this is an inorganic process, but it involves organic, and this is inorganic. So these two, the exchange of carbon between the oceans and the atmosphere and the oxidation during weathering actually do involve organic carbon. Okay, describe the biological pump. I'll just say that it's important to look at page 58 because that defines it. It says the overall effect of photosynthesis in shallow ocean waters, of the settling of organic matter, and of decomposition in deep waters is the transfer of CO2 and nutrients from the surface waters to the deep ocean, and this is known as the biological pump. And I'm not sure about this. That seems like a strange page number, but have a look at figure 8-9. Definitely take a look at this and the page that's on. I'm not sure that's correct. My notes might be wrong. Sorry about that. So why is plate tectonics critical to the maintenance of an atmosphere-ocean reservoir that is rich in carbon? You can see figure 8-17 for this, for some information on this. And look on page 168. I suspect that this is probably 158 because I just left the one out. It's in that chapter. So plate tectonics involves the movement of the crustal plates on Earth, and thus plate tectonics is responsible for transporting marine sediments from ocean basins towards the continents. And this is where carbonate metamorphism occurs. That is, that the rocks basically go under in these subduction zones. They drive under the continents, and then plate tectonics then emits the CO back into the atmosphere at both mid-ocean ridges and via the volcanoes. So take a look at this, and that should explain how plate tectonics participates in the carbon cycle. And then finally, limestone weathering does not lead to the net removal of carbon dioxide in the atmosphere. Why not? This is because limestone or carbonate weathering is simply the opposite of carbonate precipitation. This occurs when those ocean organisms create their calcite shells. And these two chemical equations are shown on page 166. And it is seen that they have a net result of carbon. Net result of carbon is equal to 0. Thus, it's a complete cycle that does not remove any net CO2 from the atmosphere. So when the little shells create the calcite shells, they're using that CO2 or carbonate in the ocean waters. That allows more atmospheric CO2 to go into the ocean. But then when these organisms, when the limestone weathering occurs, it just releases it back into the atmosphere for a net 0. Okay, that's it for these reading questions. I hope this helped.